Section 1.4 is about transformations of graphs, and we're going to be talking about 6 parent functions. I call them the Fab 6 or the Fabulous 6 functions, and you studied these functions before, but now we're going to look at them through a pre-calculus lens, and what that means is we're going to take steps a little bit further with some different notation, but it also means that we don't have to do all those exact same steps that we did last year. So our first function is the linear function. It is a function in y equals, or f of x equals, mx plus b, that's slope-intercept form. So you have a slope of m and a y-intercept of b. And when you draw a sketch, you must include 2 points. That way you know the direction and slope of the line. Another useful form would be point slope form. Y minus y1 equals m times x minus x1. In that form, you need the slope and just any point, and you could then get from point slope form, if you get this y by itself, distributing the m and then adding y1 to both sides, that gets you slope intercept form, or y equals mx plus b form. So I think we all know what a picture of a line looks like. If we have 2 points and we draw a line, that is a linear function. Next we have our friend the quadratic. The sketch is a U-shape or a parabola. When we sketch a quadratic, we must include the vertex. And in order to calculate the vertex, the x-coordinate is x equals negative b over 2a. We then substitute that back into the function to get the y-coordinate of the vertex. Or if we're given the quadratic in vertex form, then we have the vertex there and we can make our sketch. If the quadratic is factorable, you must include the x-intercepts as well. And all quadratics start at the point 0, 0. So that would be what a quadratic looks like. A cubic one. We haven't done a lot of cubics last year. In this form, we did polynomials where maybe we had 3x intercepts, but we didn't really call them cubics. The sketch is a snake, and you only need to include the turning point, and I'll show you what that is. And the starting point, again, is at 0, 0. So a cubic function will look like this, and it kind of looks like a snake, and this right here is our turning point. And if we look real close, that turning point is when, it looks like this graph is going to curve back and come down, like right here, like that. But instead of coming down, it turns upwards and keeps going. So that's what we call the turning point, or technically it's called an inflection point. Then we have our other friend, the absolute value graph. It's a V shape. You must just include the point or the vertex of the V. And then the starting point is 0, 0. So absolute value graph looks like that. The square root function, well, it's half of a sideways parabola, and you only need the starting point, which is at 0, 0. So square root graphs look like this. And then the last one is called the inverse, or also rational function, where we have x in the denominator, and when we sketch that, we must include our asymptotes, and that happens when the denominator is equal to 0. So on our sketch, we have these asymptotes, and this graph will have 2 branches and look like that. On the next page, we're going to talk about the transformations, and your class last year may have referred to them as R, S, T when you listed the transformations. So reflecting over the x-axis, we know that happens when the number in front is negative. So in function notation, it would look like this, because now the number in front is negative. So our new function is the negative f of x function. So that's reflecting over the x-axis. What that would look like is if we had the point here of 2, 1. Oops, if this was a point 2, 1, then the reflected point would be down here at 2, -1. So reflecting over the x-axis changes the sign of the y-coordinate. So we replace y with the opposite of y. Not negative, because if it's already negative, then it becomes positive. So switch, oops, signs of y values. Now, reflecting over the y-axis, that's new for us this year. We haven't done that before. So what that will look like is that our g of x function, our new function, is going to be f of -x. So reflecting over the y-axis, our x-coordinates will change sign. So if I have a picture like this, and again the point 2, 1, the reflected point will be -2, 1. So switch signs of the x values. Right, like I said, that's new for us this year. Then stretching / shrinking, that is when we have an actual numeral in front. So g of x would equal a times f of x, and we multiply y coordinates, or y values, y coordinates by a. Now, if the absolute value, if the absolute value of a is less than 1, then we have a shrink vertically, and we call that, we're going to abbreviate that as v shrink. If the absolute value of the number in front is bigger than 1, that is a stretch vertically, and we abbreviate that v stretch. Now, translations, we can translate up, down, left, and right. So if we are translating or shifting up, that function is going to have a k value added on the outside. It's going to say plus a number. If we're shifted downwards, is going to be subtraction. We're subtracting a number on the outside. So if the number is being added or subtracted on the outside, that's a translation up or down. Then left or right is x minus h, and the h and k and a should be familiar from last year. So notice that if we're going to the right, it's minus on the inside, the opposite of what you would think. And then For left translations to the left, it's x plus h. Again, the opposite of what you would think. So that if something's asking you for the translation vector, that's h comma k. And you did talk about that in geometry, where you were translating points in the coordinate plane and you were asked for the translation vector, and that was whatever your h and k were, how far you moved left or right and up and down. And then we are going to add our h value to the x coordinates and add k to the y coordinates. And remember, adding can be adding negatives. So when I say add, that also includes adding negatives instead of saying add or subtract. So reflecting and translating are called rigid motions because the shape of the graph doesn't change at all. But when we start shrinking and stretching, that is when that is a non-rigid transformation because the shape is moving, or the shape is changing. And when you did dilations in geometry, those were non-rigid motions because the graph or the object was no longer the same size and shape. So looking at these, we're going to compare the function with the parent function. You may say, well, there's no family here. We don't know if this is quadratic or an absolute value. Well, it doesn't matter if we're asked to compare. So when we're asked to compare, we're going to do that RST stuff. For reflection, we have a negative in front, so we're going to say reflection over the x-axis. X-axis. Shrink or stretch. The numeral in front is 1/2, so we would say a vertical shrink. And then for translation, it's the opposite of what we would see on the inside, so left 1, and then on the outside of the parenthesis, it's exactly what we see, up 3. And then letter B. R, there is no reflection, so we're going to write none so that we know there's no reflection. Don't leave it blank because then we're not sure if you know what you're talking about or not. A 2 in front means vertical stretch because 2 is bigger than 1. Translation, we're going to abbreviate left 1 and down 5. Okay, so we're at the point where we can abbreviate more in pre-calculus. Okay, then the last one, we have a negative in front, so reflection is over the x-axis. I see, can we have reflection over the x and y-axis? Yeah, you can have a reflection over both. There's no number in front, so there's no shrinking or stretching. And then our translation, it is right 6 and up 2. So example 2 is going to say compare the graph of the function with the parent function f of x equals the square root of x. So you may notice for this one, the x isn't first. We have a negative in front of it. Having a negative in front of the x makes things a little bit more complicated because what we have to do is factor out that negative. Okay, so first I'm going to rearrange this like that. I'm going to say, oh, okay, that plus 2 means we're shifted to the left 2, but we have to factor out the negative 1, which then makes that minus 2. So this blue function is what we're going to be dealing with. So R for reflection, there is a reflection over the y-axis this time because we have this negative in front. Shrink or stretch, there is no shrink or stretch because there's no number in front. And our translation, we only have a number underneath the radical or in parentheses with the x. So that means we are going to be shifted right 2. Letter B, we have a reflection over the x-axis, since there's the negatives in front of the radical. Shrink or stretch, there is no shrink or stretch because there's no numeral there. And then our translation is just up 3. Then letter C, well, we got a lot going on with letter C. So let's rewrite this though. When we factor out that negative, it's going to be x plus 4 under the radical and then minus 2 on the outside. So this actually has a reflection over the x-axis and the y-axis. Shrink or stretch, because it's a 1/4 in front, it is a vertical shrink. And then our translation is left 4 and down 2. So look at each part individually to get the RST list. All right, now example number 3. There's a lot to do with each of these examples. And the table is there more or less to help you organize your information. So it says the function g is related to one of the 6 parent functions. We're going to identify which of the parent functions it is, describe the transformations, create an RST table of ordered pairs. If we need to, sketch the graph, and then use function notation to write it in terms of the parent function. So what that means is that we're kind of going to go backwards from what we did right here, okay, where I gave you the function and we had to write the RST. We're then going to go backwards. All right, so this is a cubic function because we have a third power, so it's f of x equals x to the third. We have no reflections because there's no negative in front. We have a vertical stretch by 3. And then our translation is left 2, down 4. Okay. So now the table, and like I said, at some point you may be able to do this table without writing it down, but I'm going to show you how it can help. For cubic functions, on the very first page, we know that we have 0, 0. We aren't reflecting anything, so we don't need anything in the R table, but our vertical stretch we have by 3. So we're going to multiply the y-coordinate by 3, which still gives us 0, 0, and then translating it, we're going to translate this point 0, 0, left 2 and down 4. So we're going to plot the point -2, -4. So that's our point. And remember we talked about how a cubic function, it kind of is a snake-like thing where it curves and turns back up. So that's how a cubic function should look. If you just draw a line, that's going to be incorrect, and you're going to lose a good amount of points because you should recognize that this is a cubic function, and if you draw me a line, a linear function, those don't match up. So now the fifth one, write it in terms of, use function notation to write g of x in terms of the parent function. So what that will look like is g of x equals, we have a stretch of 3. So 3 times f of x, and we are shifted left 2, so we need to have plus 2 on the inside. And then down 4 means we must have minus 4 on the outside. So that's written in function notation that tells us that our function is the vertical stretch by 3, shifted to the left 2, and down 4. So the next one is a square root function, where we're going to have to factor out a negative. So this means we're going to be reflecting over the y-axis, which means when we draw this, we're going to have to go in the other direction than what we did up here for the square root function. So yeah, we're drawing fewer points, but when we're drawing fewer points, it means we have to do a little bit more thinking about what this function should look like. So our parent function is a square root of x. Reflection, we do have a reflection over the y-axis. Shrink or stretch, none. And our translation is going to be right 3 and down 1. All right, so parent function, 0, 0, reflecting. Well, when we reflect our parent, our starting point 0, 0, it's always going to be 0, 0. But let's also write down, though, that we do have a reflection over the y-axis. And then when we translate that point, we don't have a shrink or stretch. When we translate that point, it's going to be right 3 and down 1. So that's our starting point. And normally the square root function looks like that, but because we are reflecting over the y-axis, it actually goes this way. It goes to the left. And then the last part, g of x is equal to f of negative x plus 3 minus 1. And again, the reason it's plus 3 is that when we factor out that negative, that will give us the minus sign right there. So that would be our transformation function to use. All right, then the last one, this is an absolute value function. So f of x equals the absolute value of x. Reflection, we do have a reflection over the x-axis. So again, when we draw our v, our absolute value v, we got to open downwards. Shrink or stretch, we have a vertical shrink. And our translation is going to be, left 3 and down 2. So 0, 0. And this is why I'm saying you may not necessarily need this table every time. We have x-axis. We have 1/2. So 0, 0, 0, 0. And then our translation was left 3 and down 2. So our point at 0, 0 is going to go down to negative 3, comma, negative 2. So 1, 2, 3, 1, 2. And since, again, we're doing a rough sketch We're not looking for perfection, we're just looking at an idea of what is this function doing. And then the last part, g of x is equal to negative 1/2 f of x plus 3 minus 2. Because again, this is telling us what are we doing to the parent function. We are reflecting over the x-axis. We are multiplying the y values by 1/2. We are translating right 3 and then down 2. So this way of writing our functions is super critical going forward because that can be applied to any function, not just these Fab 6 functions. All right, so thanks for watching. Make sure to like the video and subscribe.